Hi everybody, welcome. My name is Ken Janda. I have the huge honor to be the Dean of Physical Sciences here at UC Irvine, and I'm just delighted to welcome such a great crowd to hear Stephen Chu. Especially a special welcome to our school supporters who help make things like this happen, but an even bigger welcome to the future anteaters who are here tonight. And we hope you're inspired to study science, maybe engineering, and make a difference in the world. So before Dr. Chu tells us how we can survive into the 21st century, I would like to introduce our provost, Professor Enrique Lavernia. So Provost Lavernia, did I just do something? Yeah. Never trust a dean. Provost Lavernia started here at UC Irvine in 1987 as an assistant professor of materials science. He rose quickly through the ranks and became a chancellor's professor and chair of the department before UC Davis hired him away as dean of their College of Engineering. We were lucky enough to recruit him back here this summer to be our provost and executive vice chancellor. And for those of you who don't understand academic gobbledygook, that means he runs the academic part of the show and is lucky enough to be my boss. So without further ado, Provost Lavernia.
Well, good evening, everyone, and on behalf of the faculty, staff, and students of the UC Irvine campus, I want to welcome you to the second annual lecture honoring the memory of Fred Reines, our founding dean of the School of Physical Sciences. I'm particularly delighted to both thank and welcome Professor Stephen Chu, who will be introduced officially in a few minutes. 50 years ago, Professor Reines came to UCI, arriving with already a sterling reputation for his work in the theoretical division of Manhattan's project, Los Alamos Laboratory. He did his work in the area of neutrinos. You see, in 1995, UCI was electrified by the announcement that not one, but two of its faculty members won Nobel Prizes. One in chemistry, Sherwood Rowland, and one in physics, Frederick Reines. It's the first time that it had happened for two faculty members in different fields at a public university. Reines' Nobel Prize was for the first observation of a neutrino particle. You see, neutrinos are all around us, and in fact, it's been argued that neutrinos can cross the entire planet without interacting with anything. So, theoretical predictions stated that it would be nearly impossible to detect them. It took somebody of Reines' creativity and caliber to develop the sensors to detect them. Today, neutrinos continue to be an important subject in physics research. In fact, the Nobel Prize last fall was awarded for research related to neutrinos, and a number of UCI faculty members were acknowledged as having contributed to the discovery, and this was recognized by the 2016 Breakthrough Prize in Fundamental Physics. Here at UCI, Reines launched an incredible tradition of asking questions about our universe, and today we stand with one of our greatest, Stephen Chu, who will join us. Thank you.
So to formally introduce Professor Chu, I'm going to call on Peter Taborik, the chair of the Department of Physics and Astronomy. So Professor Taborik got his undergraduate degree at Harvey Mudd College, his PhD at Caltech, where I think we met. Long story short. And he came to UC, after working at AT&T Bell Labs and Texas Instruments, he came to UC Irvine in 1989 to join our Faculty of Physics, now Physics and Astronomy. Professor Taborik.
Okay, good evening and welcome to the second Reines lecture. who's going to be given in a few minutes by Stephen Chu. As you've probably undoubtedly read in your program, there's two important facts about Steve Chu, one of which is that he got the Nobel Prize in 1997, and the second is that he was the Secretary of Energy in the first part of the Obama administration. And I'd like to spend a few minutes to tell you a few other highlights of his milestones in his career. So Professor Chu is an experimental physicist, and many of the things he does involve the interaction of light with atoms and molecules. He got his PhD from UC Berkeley, and then a few years later he went to Bell Laboratories, where he and I crossed paths and got to know each other when we both worked there in the early 80s. While he was there at Bell Labs, he's an expert in spectroscopy, and he did some amazing experiments on the spectroscopy of positronium, which is a bound state of an electron and an anti-electron. And this is a super hard experiment. It was a tour de force, and he managed to measure the energy levels to parts per billion. One of the things that makes experiments like that hard is that atoms and molecules tend to move very rapidly and chaotically. And so even the molecules in the air in this room are moving at over 1,000 miles an hour, and that makes precise measurements difficult. The experiments that led to his Nobel Prize was a very clever scheme to slow atoms down. And the basic idea was to use cross laser beams. So laser beams going north, south, east, west, and up and down, and all tuned to a resonance, near a resonance of an atom. And the basic idea was that if the atom tried to move, it would absorb a photon and get kicked in the other direction. And because of that, it was very difficult for an atom to move in this cross laser field. And the whole thing it was marketed very cleverly and given the name optical molasses, because the thing just could not move. The idea, the technique for slowing these atoms down formed the basis for extremely precise clocks and frequency standards, and it also became the basis for several subsequent Nobel Prizes that looked at the state of these quantum cold gases. So Steve Chu left Bell Labs in 1987 and moved to Stanford to become a professor of physics. And he had a superstar academic career. He won, and I can't give you the list, he won numerous prizes and became a member of many national academies and so on, and that culminated in the Nobel Prize in 1997. Most world-class scientists are intensely focused, nerdy sort of people who actually have a hard time dealing with the rest of the world. Lots of people have Nobel Prizes. The truly amazing thing about Steve Chu is that he combines this Nobel-caliber science with the ability to see the interconnections between various disciplines, to communicate with a broad range of people, and to lead and inspire organizations. Steve held several leadership positions at Bell Labs and at Stanford, and in 2004 he was recruited back to his alma mater, Berkeley, to become the director of the Lawrence Berkeley National Laboratory, which is a laboratory with 4,000 people that covers the spectrum between genomics and nuclear physics. At the Berkeley lab, Chu became increasingly interested in issues of climate and energy, and basically in how, the issues of how we produce, use, and transport energy. And he was so good at it, and his academic credentials were so sterling, that President Obama appointed him Secretary of Energy. During his time at DOE, he became an expert in all aspects of climate and energy, ranging from biofuels, home insulation, fracking, wind, solar, batteries, and nuclear energy. He managed to explain these things to audiences that ranged from skeptical U.S. senators to Jon Stewart on The Daily Show. He went back to academic life at Stanford in 2013 as a professor of physics and molecular and cellular biology, but he's continued to work and write about energy and sustainability issues. Please welcome tonight's speaker, Steve Chu.
So, thank you very much. I'm going to reset my clock to know when I'm going to start. It's a pleasure to be here, to be visiting Irvine, seeing old friends like Peter, but also to give the Rhinus lecture, who was certainly a giant in physics. You already saw the preview of what I'm going to be talking about. So I'm going to talk very briefly about the risks of climate change, particularly measurements, recent measurements that some of you may not know about. Spend some time talking about trends in oil and natural gas, and finally, how science and technology can really show the way. So here we go. So talk about the risks of climate change. So the first thing I want to talk about is the climate changing. And so this is some data taken between 1850 and 2000 and 15. And you look at this and you say, this is the average surface temperature of the land and the oceans over this period of time, and the temperature seems to be going up. At least you'd think it could be seen as temperature going up, but when I was in Washington, D.C. for 4 1/3 years, much was said about the following, that it's not going up. See, in the last 15 years or so, it plateaued. Now, remarkably, they didn't talk about this plateau, which is much longer, because if you did, you have to say something about what happened in between. So they just talked about the last 15 years. So, but there is a question, and one of the criticisms was correct. The climate models did not predict that this temperature would plateau as it did in that period of time. And so that was an issue. And so the climate skeptics would say, well, the climate models can't be trusted because they were predicting the temperature to increase and it didn't. Therefore, their predictions of the risks cannot be trusted, and so why worry? So let me tell you a little bit about this. What does this have to do with anything? Well, I spent a summer in 2010, a large fraction of the summer in Houston, helping BP stop an oil spill. It's not like the Department of Energy is actually mandated to help stop oil spills. In fact, we have no jurisdiction. I'd made a suggestion, the president had heard about it, and after one cabinet meeting early at the end of April, he says, Chu, get down there and help them stop the oil spill. Yes, sir. All right, so 1 mile deep in the ocean, oil and gas were coming out in great quantities. And there's something about this I have to remind you about, but you probably don't know. The surface temperature at the Gulf of Mexico during that summer was about 86 degrees Fahrenheit. It's like a warm bathtub. Where the oil was leaking out 1 mile deep, it was 1 degree centigrade above freezing. It stays that way all year round. The bottom of the ocean, and this is not the bottom of the ocean, this is only 1 mile deep, is cold. All right? So hold that thought. And so people began to suspect maybe the heat went into the ocean, and then maybe the mixing wasn't predicted well. So they said, well, let's drop some buoys, these yellow things. We don't drop him, we drop these things. And they're dropped from airplanes, and they take a surface temperature of the ocean and the salinity. Then they go down, and they go further and further down. And these series of these went 2 kilometers deep, and every 10 days they resurface, and they use this antenna, and they radio satellite the data to some central place. If you just drop one, it's not good enough, because who would trust that? So you've got to drop a couple. These are the numbers. So these are the different countries participate in this. So in 1 degree latitude and longitude around the whole world, these things have been measuring temperatures of the ocean, not only the surface, but down to 2 kilometers. And to make a long story short, what came out was the following. This was a paper published in 2015. Between the years 2006 and 2014, because most of the ocean is in the southern hemisphere, not the northern hemisphere, it's seasonal, so the temperature goes up and down, up and down. But this is the temperature, the heat content of the ocean. And you will be happy and relieved to know that energy is conserved. What do I mean by that? The sun has solar oscillations every 11 years, but on average over 30 or 40 years, as measured by satellite, the average energy hitting the Earth is roughly the same. the energy leaving the Earth cannot be the same because the greenhouse gas effect is truly real. So less energy is being radiated. Where did it go? It went into the ocean. The climate models did not predict the subtle mixing time. It's a very long mixing time, 50 or 100 years. But the measurements say, at least energy is conserved. That's good. Okay, so do we understand everything about the climate? No, but we actually know that energy is conserved. Okay, another couple questions. Are the glaciers truly melting? Is the sea really rising? Short answer is yes, but let me describe how one measures it. You can measure it by going and taking photographs. If you were alive in 1941 and went to Muir Glacier in Alaska, this is what you would have seen in August of 1941. This is what you see in August of 2004. It looks different. And lots of places in the world, they look different, but this is what we call anecdotal evidence. So is there a better way of measuring whether the glaciers average around the world are changing? And the answer is yes. And this is remarkable how we do it. We use satellites. They're in polar orbit. So as the Earth rotates and these satellites go around, if there are local changes in the acceleration due to gravity, it makes the orbit of the satellites change a little bit. And you use a pair of satellites, and so as let's say these satellites are about to traverse over Greenland, where there may be a changing ice sheet, their orbits may wobble a little bit, and so the distance, the height of the satellite orbits are measured by GPS. The distance between the satellites are measured to a small fraction of the width of a human hair. Okay? Like a tenth the width of a human hair. If you're, middle-aged, if you're younger, it's, never mind. Anyway, so that measures changes in the acceleration due to gravity. There's another thing you have to measure, which is if the glaciers are changing, if something's changing, the height is changing, and so that also affects the local perturbation of gravity. So you have very precise radar and actually laser ranging to find out how the heights are changing. Okay? So these are the two measurements we use. This is what you see. This is a map of Greenland. Where you see red, you see an increase in mass. In case you're colorblind, you don't see red. Where you see blue and purple is a decrease in the local acceleration due to gravity. And you see a lot of purple. The resolution is summer, winter, summer, winter. This is 2002, 2012. The ice mass is decreasing. This is an exquisitely precise measurement. The scale here is a change in the thickness of this red arrow is 20 centimeters over 2 kilometers of ice. Okay? But the ice mass is decreasing, and it's accelerating the decrease in the ice mass. This is another recent data. I think this was published year 2009. This is Antarctica. This is the ice, the western shelf of Antarctica, losing lots and lots of ice. It was thought originally that the eastern part was gaining a little ice, but with the combined measurements, they say that's roughly the same. Lots of ice being lost. If ice on land slides off and melts, the sea level rises. And so the question is, how much does it rise? Again, we don't really know. However, and it's hard to predict. However, let's use history as a rough predictor of what might happen. And you ask the question, what happened in the last warm period? It was an ice age before that. The last warm period was 129,000 to 116,000 years ago. It was only 1 degree warmer than it is today. And by measuring the fossil record along the coasts around the world, and you have to average around the world because land rises, land subsides, so it's a global average. With 95% confidence, the sea level, 1 degree warmer than today, was at least 6.5 meters higher. Somewhere between 5 and 10 meters, only 1 degree warmer than today. That was our previous history. Now you're probably scratching your head and saying, no, I heard IPCC says it's only, like a half a meter by the end of this century. Absolutely true. except for two things. They don't say what's going to happen in the new equilibrium, 1 degree warmer. They only say what's going to happen in this century, 2100. They also say in their full report, yes, this is what could happen. And so, in fact, this is what did happen. So now, at 6 degrees warmer, we know that all of Antarctica melts. And so at 6 degrees warmer, the sea level rises about 200 feet higher, averaged around the world. But, you know, even 7 or 8 meters is a lot. You know, Old London is now underwater. Harvard would be underwater. I just checked, and where would Stanford be? Well, we would have a beautiful bay view. Not, you know, but we would be feel very sorry about Harvard. But seriously, all joking aside, the question is, how long would it take to get to this? And again, we don't know. We thought maybe it'd take several hundred years to a millennia, but the recent data from Antarctica Western Shelf, it's melting far faster than we thought even 5 years ago that would be possible. And so we don't know is the real answer, but it's scary because the preliminary data is saying it might get there far sooner. Okay, so let me just say this is the history, remind you of the history. This is the present time. This is looking backward in time. This is a proxy for the temperature averaged. This is methane, carbon dioxide. By the way, we're up here today. So we're off the charts, not only for the last 800,000 years, but we're actually off the charts for the last 3 million years. Now, you can say, well, what happened here? This is warm period. We're in another warm period. This was an ice age. You can't blame this on humans. So, of course, the climate changes, and it changes naturally. So what's the big deal? The big deal is, well, we're off the charts, and at a time that doesn't show up in geological times. So then the question is, does this have anything to do with, oh, by the way, this is what I mean by 1 degree, 1.5 degrees warmer. We're here. We're actually a little warmer than that. So that's the issue. Now I'm going to explain to you why we think this is not due to natural variations in the climate that we've seen in the last not only 800,000 years, but millions of years ago. The climate of the Earth does change. So why all of a sudden are we the culprits? Why do you blame it on us when you didn't blame it on Neanderthal men and women, 50,000 years ago? And it has to do with something which I will explain to you. So before you can look at me, don't look at this just yet. I'm, in fact, I'll grab your attention. I have to explain to you about radioactive dating. So you've probably all of you in the audience, or most of you, have heard about radioactive dating like carbon-14. So let me explain to you how that works. The isotope of carbon, carbon-14, is made in the upper atmosphere due to cosmic ray bombardment of nitrogen, and it turns nitrogen into carbon. The carbon has a finite lifetime. It's 5,700 years. It decays. Okay, but during that time, that carbon diffuses down from the upper atmosphere down into the biosphere. It's taken up by everything, both inorganic and organic carbon. You and I have carbon-14 in our bodies, all right? But we're in equilibrium with our environment because we're taking in carbon, we're putting out carbon, we're doing all this stuff, we eat stuff, okay? Now suppose you die and they put you in a really good coffin for 1 million years. And you're no longer in communication with the rest of the environment. You're now sequestered somewhere down there. But your carbon-14 is gone because it's only 5,700 years, one lifetime. After 10 lifetimes, 57,000 years, it's gone. 1 million years, it's really gone. Now we take you up and we put you in a power plant, you and all your neighbors, and burn you as fossil fuel. If there's enough fossilized carbon that's been underground for more than 50,000 years, you're introducing carbon but not the radioactive component you're only introducing the stable component, like carbon-12, okay? It's a small effect unless you're introducing lots of carbon-12. And so here's the amazing thing. It also turns out, I won't go into this, carbon-13, a stable isotope of carbon, also is an indicator, but I'll just stick with carbon-14. This is the carbon dioxide emissions as you go in time from the beginning of the Industrial Revolution, going up and up and up, and carbon-14 is getting diluted down and down and down. Okay, but this is 1950. Well, we're not in 1950, we're in 2015, so why am I not showing you that data? Well, I'll show you the data. From 1950 to 2000, and this is 2010, something happened to the carbon-14 in the atmosphere. It just shot up like that. What's that due to? Hydrogen bomb testing. So the United States and the Soviet Union started exploding hydrogen bombs, and that carbon, and that introduced a lot of carbon-14 in the atmosphere. They're exploding mostly in the northern hemisphere. And so this is the northern hemisphere, and this is just summer-winter variations. The resolution was that good. There's a delay in the mixing time between the northern hemisphere and the southern hemisphere. It was about 1 year. And so you see the southern hemisphere picking it up. Then this carbon-14 gets absorbed in the ocean. Most of the carbon emitted by fossil fuel, over half of it gets absorbed in the ocean as inorganic carbon by carbonates. Soda water is acidic. And so the ocean begins to absorb the carbon. It's declining. Everything looks pretty good. So here's where we are. But then you look at the rate of decline of that, and you say, is that consistent with just the carbon-14 being absorbed from all those above-ground nuclear tests and it being absorbed in the ocean? Is that matched? And the answer is no. It's decreasing too fast. What does it match? It matches this mixing plus the amount of fossil fuel to within 20-25%. You just count up the amount of carbon we put in the air with fossil fuel, it matches. Okay? So this is what we call the smoking gun. There's several smoking guns that say this carbon couldn't be carbon going into trees, the trees die, the microbes recirculate it back in carbon dioxide and methane, goes back into, that has a 100-year time scale. Oceans, hundreds to 1,000-year time scale. Okay, but remember, carbon-14 has a 5,700-year lifetime. So you would have had to have put it away for many tens of thousands of years to millions of years and have it reemerge. Stuff like this which says it appears to be human this time. Okay? It cannot be natural cycling. All right, let me continue. This is, seems like a non sequitur. This is tobacco use US, 1900 to 2005. In 1900, we did not smoke much as a country. This is the per capita consumption of cigarettes among males, peaked around 1960. During its peak, the average consumption of cigarettes among males was 225 packs a year, including the non-smokers. Averaged over all males, it was 225 packs a year. There are 365 days in a year, just in case you want to, more than a pack, half a pack a day, average. In the 1940s and 50s, something started to happen. An extremely rare cancer became a prevalent cancer, lung cancer. And so the medical community said, what the heck is going on? All of a sudden people are starting to keel over from lung cancer, males. And by the 60s, they said, this may not be a coincidence. And by 1964, the Surgeon General said there's enough epidemiological evidence. That means just based on correlations of things, and when you try to rule out other correlations, that we think that cigarette smoking causes cancer. And so they put this warning label on cigarette packs saying, caution, cigarette smoking may be hazardous to your health. Okay? The next Surgeon General wanted to put in a more stringent warning. cautioned cigarette smoking is hazardous to your health, but it was during an administration that was unpopular, so the guy got fired. Okay. So there's a delay of 25 years by the time you start smoking, by the time you die of lung cancer. Lung cancer, if not caught early enough, is still a fatal disease. We now, this is female deaths. Now, is this genetic difference? I don't know, but females start smoking later. But so a big campaign to discourage smoking in the United States among school children, followed by a decline in cigarette smoking deaths due to cancer. But we also know if you smoke a pack a day, you have a 25 times higher chance of getting lung cancer. Not 25%, 25 times higher. Coronary heart disease, 2 or 4 times stroke, 2 or 4 times kidney disease, everything. It's the biggest single threat to your health that's preventable is not to smoke. Okay? So that's what we know today. What does this have to do with climate change? Well, the delay time from the time you start smoking to when you get lung cancer and die of it is not known. From the time we put carbon up in the atmosphere, what we've already done to what the new equilibrium would be if we put no more carbon due to human activity, from here on in, 0, it would take maybe 100 years, maybe 50 years, maybe 200 years, we don't know, to reach the new equilibrium. During that time, the damage may have been done. So we don't know. Because in smoking, it's multiple mutations that cause the cancer eventually. What else don't we know? There's secondary smoke. Well, climate change is all secondary smoke. Because the people who will suffer from most of the stuff in adverse climate change will be people who aren't alive today. And the best estimates, again, large uncertainties, is that eventually the carbon gets reabsorbed because as it warms up and there's more carbon dioxide, there's going to be more plant life, if all other things being equal. We're trying to fix that with deforestation, but never mind that. The natural response, the ocean is absorbing the carbon. It's become more acidic. It's 30% more acidic than it was before the start of the Industrial Revolution. 30% more acidic. These are not small effects. These are really big effects. And so it will continue to absorb carbon, and the plant life will absorb carbon and mineralize it slowly. That's, in fact, where fossil fuel comes from. So, but here's the very distressing thing. If you're a smoker, you bear the risk yourself personally, right? If you continue to smoke, you bear that risk. Your great-grandchildren don't bear that risk. This is different because I see it as the following. I like smoking, and there's no proof, absolute proof, that all these bad things may happen. And so since it's just, theory, why should I take a hit in my lifestyle? Smoking relaxes me. And, what happens to my great-grandchildren? Not my problem. Okay, so that's so far what society has chosen. Not my problem. And not only not my problem, it's forget about your great-grandchildren and great-great-grandchildren. And the ones halfway around the world we'll never meet, not my problem. So this is a problem. Okay, so, all right, there's all sorts of things that could go wrong. I will stress we don't know. There are huge uncertainties, but it's like now we've had 20 years of science telling us smoking is bad for you. We've got 20 years saying, the climate seems to be changing and there are risks. So what are the choices? Maybe not be bad for everybody, but on average, the choices are it could be bad, it could be very bad, or it could be catastrophic. Okay? It's not, it's okay. Or it's going to be better. All right. Here's another thing that's a little bit scary to me. It roughly turns out that in terms of the amount of carbon in the atmosphere, in order to keep a low 1 2 degrees below the start of the Industrial Revolution, now 1 degree below where we are today, you are only allowed to emit 1 trillion tons of carbon. Okay? We're more than halfway there. And oh, by the way, if we continue emitting at the rate we're emitting today, the rest of that is used up in 30 years. But remember, 1 degree warmer than today, at least historical record says 5 to 10 meters higher sea level. Okay? So this is not a small effect. This is not, oh, we can weather this one. So even staying in 1 or 2 degrees is very bad, very scary. So why aren't you saying, why are we not calling for stay to 0? And it's just because we can't change on a dime. So whether we're going to go bust through this in 30 years' time or 50 or 60 years' time, I don't know, but it will be sometime around that time. All right. Let me talk about energy trends in oil and natural gas. I'm going to quote some people I admire very much. They wrote, "Our ability to find and extract fossil fuels continues to improve, and economically recoverable reservoirs around the world are likely to keep pace with rising demand for decades." This is talking about oil, natural gas. I said that. Okay, now, why did, and I and Arun Manjari, we wrote a Nature paper, an 8-page Nature paper talking about this. Why did we say that? So let me remind you of what's been going on. This is U.S. oil production from 1945. I'm going to take you through 2014. U.S. oil production peaked around 1970, and it became more economical to go abroad and find cheaper, more easily recoverable resources. Despite the great Alaskan oil find, it still declined. But you see that little thing on the right-hand side, that little green thing called type? By 2013, U.S. production rose to 7.5 million barrels a day, and by 2014, it went to 8.5 million barrels a day. The increase due to tight oil, which is oil released from fracturing rock with hydraulic fracturing, turned out to be 4.5 million barrels a day, just the increase, which is more oil produced anywhere in the world except for 3 countries: Saudi Arabia, Russia, and the United States. More than Iran, more than Iraq, or both of them combined, actually. More than Venezuela, more than anything. The increase. All right. But there's much more oil out there than just the oil that can be released from fracturing rock. There's untapped heavy oil. There's untapped offshore oil. There's untapped Arctic oil. Offshore oil, drilling a mile deep in the ocean is now routine, and now going to 2 miles deep, going to Arctic oil sands. So all these are what are called unconventional resources that are certainly recoverable at $100 a barrel. Many of them are actually recoverable at $60 a barrel. Some of them are definitely not recoverable at $40 or $30 a barrel. Okay. But, so lots of oil, swimming in oil. So let me quote another quote. "The Stone Age came to an end, but not for lack of stones. And the Oil Age will end, but not for lack of oil." So it turns out a former Saudi oil minister said this, Sheikh Yamani. But that's not why he's the former Saudi minister. What he was saying is, you don't look at all the stones around the ground and say, stranded assets. Not every stone has to be turned into an arrowhead or an axe. Okay? You transition to metal, and there's better ways to go about it. The converse is the following. You transition to better solutions, but if you don't find better solutions, the oil and gas come out of the ground. And so this is a sobering thought. If you're sitting on billions upon billions, about trillions of dollars of oil and gas underneath the ground, it comes out. Unless you find a better solution, which means a better solution means a cheaper solution. Okay? All right, so let's talk about science and technology. What do you want to do about it? Well, you stop wasting energy, use energy more efficiently, and then I'll talk about clean energy resources. So, this is a paper that my colleagues and I published recently, and it's a study of the following. These are refrigerators, room air conditionings, clothes washing, and central air conditioning. Let me see if I push the button too fast. Here we are. And so this is the cost of buying a refrigerator and operating it, the cost of energy over a long period of time. And I'm plotting this in terms of the cost every time you double the number of shipments of refrigerators or washing machines or whatever, the cost goes down by a certain percentage, whatever it is. This is called a learning curve. And so what are these arrows? These arrows are times when, starting with California, appliance efficiency standards started to be introduced. And it was not introduced just once, but several times, because as the technology got better, one found that you can have better efficiency standards and it wouldn't cost as much. So not surprisingly, the cost of buying and operating an appliance would go down. What's the red? The red is the purchase price. That was surprising, because you'd think that when you put in efficiency standards, the cost of buying the thing would be more expensive, because it had to be better. It couldn't waste as much energy. And so we were all excited about this. We submitted the paper first to Science magazine. It went out for review. One of the reviewers said, "This is amazing. This is amazing that it could happen. And of course it should be published." The other two reviewers said, "I don't care what these people say. This is impossible." But it's data. No. So then I realized that physicists and economists think differently. Now, how much energy did this save? Just refrigerators alone, the cost declined 28% for each doubling of production, and the energy saved by the time you're out here is the energy produced by the Three Gorges dams, which is the biggest hydroelectric dam, or all the coal plants in Ohio. It's a big deal. And not wasting energy, but you're saving energy. So I'm a professor. Here's a surprise quiz. How many free market economists does it take to change a light bulb? None. If the light bulb needed changing, the free market would have done it. So, so the reaction among the free market economists was, this is impossible, because how could manufacturers manufacture a more expensive refrigerator that wasted more energy? Therefore, this may work in practice, but it doesn't work in theory, so it must be wrong. Fine. Okay. I can theorize about why it happened. The theory goes something like this. A new standard means you go back to the drawing board and you design a more efficient thing, a better compressor, a smaller compressor, better insulation, things like that. But that's just theory. The fact is, this is what the cost did. And that's the only, in the last analysis, that's the only important thing, that efficiency standards actually drive innovation that makes the cost of the appliance less money. All right, so let me talk about, and this is true of many, many things, but let me talk about clean energy sources and wind energy. This is a wind map of the United States. We have some of the best wind in the world. This is Canada, this is the United States, good wind offshore. The map doesn't have fine enough resolution. This is Washington, D.C., where there's lots of wind, but it's... when I was Secretary of Energy, I wasn't allowed to say stuff like that. So, but anyway, we have great wind in places around the world. This is the cost of wind power generation. It had a little bump upwards. There's a supply bump as it got to be really popular, but it's working its way out. It's going down. This is the amount of installed wind capacity. The amazing thing about wind farms today in the United States, in the Midwest, is when you build a wind farm, you have to raise couple $100 million. It's not to build a big farm. Before anyone gives you a couple $100 million, you have to have a contract that says a utility company or several utility companies will buy my wind at a certain price. The price is now less than 2.5 cents a kilowatt hour. New natural gas, if you built a new natural gas plant, and if the cost of natural gas were $4 million BTU, which would be historically way low, it's now, in case you're wondering, it's even less than 3 at the moment. But no one expects natural gas to be less than something around then in the coming decades. It's more money. Okay, now there is a wind production tax credit for this. If you back that out and try to estimate it, they're comparable. So wind today in the best sites in the United States is going to be better than natural gas, certainly within a decade. Okay? The technology is getting better. These are the standard heights where it used to be 80 meters, and the best wind sites are only a very, very small fraction of the, let's see, where am I talking about? Here. So you have, this is all the landmass of the United States, taking away the national parks and everything else. And the really good wind sites, there's only a very small fraction that have, let's say, 30 or 40% duty cycle. But the turbines are going up higher. They're getting more reliable. And so at this height, you can have 45% duty factor. That means the turbines are spinning 45% of the time, a reasonable fraction of the United States. And when you go to 140 meters, you can get 50% duty cycle in a large fraction of the United States. And they're getting more reliable. So because of the technology, the turbines are getting better. The ones offshore are getting bigger, faster. This is an offshore 6 megawatt. A single turbine can generate 6 megawatts of electricity. The standard is going to 7.5 megawatts. This one happens to be 154 meters in diameter. That's 1.5 soccer fields. Or compare the Wright brothers' first flight, which was only 36 meters. So many hops across, much bigger than a 747 or an Airbus 380 in terms of wingspan. These are very, very big. Also getting more reliable, cheaper. But it's 2.5 times more costly. The duty cycle could be 50%. So it's really, how do you make these last for 20 or 30 years in a marine environment is going to be the crucial thing there. Solar energy, also very good. So cost of solar modules between this is a supply bump of silicon shortage, but between this peak and down here, the cost of solar modules dropped to 1/5, only 20% of the cost in 2006 to where they are today. If you go back to and start the clock when they first actually began to get deployed, the cost decrease has been more than 99%. That's a lot. Actually, 20% of what it was 6 years ago is a lot. Think of buying a car instead of $30,000 or $20,000, it's $4,000. Okay, so it's plunging. The solar contracts are actually getting very, very good. They're becoming competitive with new natural gas as well. The newest contracts being signed are 5 cents a kilowatt hour. Fantastic. And it's going to go down by at least a factor of 2. So renewable energy, wind and solar are decreasing a lot. All good news. The solar map of the world is pretty good. We don't have the best, but we're very, very good. And so what about the United States and solar? We didn't really do much solar. It bobbled along 1990, and the amount of electricity generated was essentially flat, which means no new solar was ever deployed until around here, and then something happened. Well, a couple things happened. Now, you could argue that correlation does not mean causation, just like the tobacco companies argued that. But you'd be wrong. In this case, because I had a big loan program, and we made over $5 billion $10 billion of loans that I had to sign off on. The famous failure with Solyndra. It was a solar manufacturing company that went bankrupt. But if you include all the losses to our loan program and you put back all the gains, how did we do? Well, I'm sad to say that we're going to make the U.S. government about $5 billion. We weren't trying to make the government any money because I was only allowed to charge 1.5 percentage points interest. And so in 2009 to 2013, we didn't do better in VC. We did better in Wall Street at this ridiculously low interest rate. Why? How did we do so well? Because much of our money went into loans for large wind and solar farms, but we wouldn't loan money until they had a signed power purchase agreement. And once you have a signed power purchase agreement, you build the thing, and if you're reasonably on time, on budget, then there's no more risk. And that's what happened. We also loaned $6 billion to Ford Motor Company. They're going to pay us back, okay, with 1.5% interest. We loaned to Tesla. Without that, Ford would have gone bankrupt, Tesla would have gone bankrupt, and Tesla already paid us back in full. So we're, so net, we did okay, but we actually got major solar and wind farms deployed, but the good news is they don't need the loans anymore. They're now considered a safe enough investment that private sector will do this. So it served its purpose, that it showed that you can build these things on time, on budget, and they're good investments. Warren Buffett, Berkshire Hathaway bought two of our solar farms. After it was constructed, he said, this looks like a safe investment. I can get 8% return on capital. I'll take it. I will take 4% myself, but anyway. Okay, so here's my projection for what's going to happen in wind and solar. By 2020, without subsidy, it'll be probably 3 cents a kilowatt hour. So it becomes lowest cost. By 2030 to 35, it drops again to 2 cents a kilowatt hour. It becomes really low cost, no competitor. Because fossil fuel in the long run will actually tend to get more expensive because we run out. So we have to get better at finding more rare, unusual stuff. And so the technology of finding the rare, unusual stuff is getting better, so it will keep price steady. But this stuff keeps on getting cheaper because the fundamental fuel is sun and wind, and that fuel is free. However, we're only about 5% wind today, US generated, not nameplate capacity, real generated electricity used. It's 5%. It's going to pass hydropower in the United States within a year. We're 6.5% hydro. The combination of wind and solar will be easily 10, 15% within a decade. Good news. But if you think about a world of 50% wind and solar, sometimes the wind doesn't blow, the sun doesn't shine, so you need backup power, and you need an enhanced transmission and distribution system to manage two-way flows. So when it is shining or blowing, you can shut off the other things, and you need energy storage. So let me talk about some of these issues. First, let me talk about why aren't the utility companies excited about solar being so cheap? And what the reason they're not is they're used to a model where if our customers want electricity, you just fire up the boiler and you generate more electricity. So they like to use energy on demand as the thing. It doesn't require technical innovation. And to be candid, if you're a stellar science or engineering student at a place like Irvine or Stanford or you name it, your goal is not to say, I want to grow up and work for a utility company. You might want to work for Google or Facebook or someplace, but not, okay. So utility companies are not known for innovation. And in fact, they most adopt new technologies at glacial speed, but that's really unfair to glaciers. Some are moving faster, but never mind. Okay, so here's the real reason why utility companies don't like solar on a home rooftop, because they're losing their best customers. The people who put solar in the roofs are usually in the upper quartile of the population, right? And those are the people who pay their bills. So when I was Secretary of Energy, I called the utility company people in, and I called the regulators in, and I sat them all down in a conference room and said, here's a plan. Why not, in order to align utility companies so they really like solar on rooftops, why don't they partner with the third-party installers? This is like SolarCity or Sunrun. They'll go and say, we will, by the way, their model is, we will install solar in your rooftop. We own the solar. We'll operate it. If it breaks, we'll pay for the fixing of it. We'll pay for your electricity. But if you sign a contract, 20 years, you can get out of it earlier. If you sell your house, there's other things. But say 20 years, we'll sell you electricity, but we'll sell it to you less than you can buy from the utility company. Is it a deal? And in a place like LA, Irvine places, they're selling at 9 cents a kilowatt hour. No out-of-pocket expenses to you. And you don't have to worry about being misinstalled or anything or breaking. It's a good deal, okay? So why not the utility go to your customer and say, could we use your roof to generate electricity and we'll sell it to you for cheaper? You can use the third-party installers to actually install it. So I said, why don't you guys, these utility companies and the regulators, why don't you let them do this? This is not a new idea. I used to work for AT&T Bell Laboratories. That phone, that beautiful, beautiful phone, was owned by the phone company. It was leased to their customers. And if it broke, they fixed it. And you notice those things never broke. They really didn't break for 20 or 30 years. They just, you could slam them on the floor, you can do all sorts of things. The only thing that broke was that cord. As soon as they stopped owning it and stopped leasing it, but you owned it, they suddenly broke every 2 years. But never mind. The point is that the utility company went behind the meter, but they could actually own the thing. And so why not let the utility companies own the solar and the batteries in the garage? What's in it for the homeowner? They get to buy electricity for less money. And within a decade, batteries are going to get really cheap. Now, 12 kilowatt hours of local storage. If you have a major blackout, what do you want? You want to be able to turn your LEDs and compact fluorescent light bulbs on. You can't run your air conditioner, but you can run a fan. You can run your refrigerator, and you can operate TVs for a couple hours. And you don't have to stumble around in the dark. So to have blackout immunity at that level for a week is pretty good, okay? Especially the refrigerator part and the fan part. You know, when it gets really hot and it gets really stinky, your food gets really stinky, it's bad. Okay, that's in it for the homeowner. Cheaper electricity, more immunity. What's in it for the utility company? First, they're in a growth industry. For the first time, all of a sudden, they're going to see an increase in customers. Secondly, they get indoor energy storage at the end of the distribution network where they want it the most. Except it's protected. It's inside. It's in a garage. It's in a business. It's not outside in the rain where, you know, all sorts of things could happen. So that's what's in it for them. I'm going to talk a little, let me talk about transmitting and distributing electricity. So the United States was the first country that actually had electrical power stations. It was Edison. He wanted to generate electricity to provide electricity so people can buy his light bulbs. And so that was the first power plant. Tesla was a competitor with Westinghouse as to whether you're going to use AC or DC, and Tesla won. We use AC because you can go to high voltage and transmit it. But the point is that if Edison and Tesla were alive today, they would come back and look at our electricity system and say, ah, I recognize everything. The transformers, the generators, everything. If Edison came back and looked at an LED light, what's this? If he looked at an iPhone or an iPod, what's that? But all the other stuff, sadly, oh yeah, that's all my old friends. I haven't changed in 100 years. So, We generate electricity locally, we use it locally. In order to use renewable energy in the most efficient way possible, you go to where it's best, where the wind is best, where the sun is best. In China, that's what they're doing. These are the high voltage, ultra high voltage electrical grid lines they're installing in China. This is their grid plan for 2020. How are they doing? Well, they've installed over 60 gigawatts of the highest voltage AC and DC lines in the world. By 2020, their current investments in just transmission lines will be $350 billion for one company state grid. From now until 2020, $350 billion in new lines. This is about how much we need for the entire United States to rebuild our electricity system. Except the regulators don't want to give us money for that, but China's managing to do this. I was having dinner with the head of this company, State Grid, and he was telling me that they're just agreed to install a 3,200-kilometer line from over here all the way to here at 1.1 megavolts, the highest in the world by far. Less than 5% of the energy would be lost in transmitting that distance, 2,000 miles, over 2,000 miles, okay? If the highest voltage lines in the United States were transmitted, 85% of the energy would be gone. We simply do not transmit energy 1,000 miles in the United States. It's all generated and used locally. And if you look at the wind map, you look at the solar map, we should be moving it 1,500, 2,000 miles. So that's something. Okay. I just want to mention it's this backup generation power. I can easily see by mid-century, 2050, we could be 50% wind and solar, but we cannot be 100% or even 80% because we have summer, winter, we have times when we have bad periods of weather. So if you had a quarter of it fossil and a quarter of it nuclear, then 3/4 of it's carbon free. And so now nuclear is a bad word for many people, especially in California and the Pacific Northeast and other places. But let me just remind you of one thing. If you look at the number of people killed per unit of electricity generated, say per terawatt hour, for one death associated with nuclear, this is the number of people that die from coal, from mining plus polluted air, okay? Per unit energy, not we generate much more by coal. So the same amount of electricity generated. Oil is a little bit better. Nuclear has the risk of about solar. How do people die of solar? Well, they're construction accidents. You know, they can die in a pickup truck as they install the stuff. So anyway, and these deaths do not include future deaths due to small particulate matter or climate change. And the scary thing is this small particulate matter may be in places like Beijing, may be equivalent to smoking a pack a day. The verdict is not in. We'll know for sure in about 10 years. But the early returns of the last 15 years is that the very small particulate matter from coal plants and from mostly diesel are as deadly as smoking a pack a day, except everybody gets to smoke from day zero. Delhi is worse. All right, energy storage. We need that for renewable energy. So I'm going to show you some really novel energy storage. Hold on to your hats. There it is. What? No, that's energy storage. When the wind blows, you pump water. And once the water is pumped out of the ground, it's ready to use. Okay? We forgot that. Okay? Because we got so used to energy on demand, you know, when you need the water, pump it out of the ground. Okay, so that's energy storage. Let me talk a little bit about batteries. The Tesla battery is pretty expensive. It's about a third of the cost of the long-range Tesla. Is about a third of the cost of the entire car, and it weighs it weighs about 1,200 pounds. And so this is a collaborator of mine in material science at Stanford, and we're working on a better battery. I don't know if we're going to get there, but right now, on the anode part of the battery, this is the average energy density. And there's silicon that's going to be new technology, but a number of companies are trying to commercialize, and there the energy density will be over here. We're happening to we're shooting for something like this. It's not ready for prime time, but what the goal would be is, and this is the technical expression for it, the battery has to last longer than the human bladder. Now, what do I mean by that? You rarely want to drive more than 200 miles without a rest stop. While the battery is charging, you're discharging. If the time it takes is about the same, you don't care, okay? So is it possible to get you to charge up 100 or maybe 200 miles in 5 or 10 minutes? And the answer is we don't know. That's the goal. And you're within a factor of 5 of this or 10 of this for sure. But if you could charge 100 miles in 15 minutes, which is totally achievable, then you don't really care anymore. Because if you have an electric vehicle that costs the same as a conventional vehicle, that can go, let's say, 300 miles, you might not ever want to go back to a conventional vehicle. Because in an electric vehicle, you can take out your smartphone and you can say, I want to go for a ride, or I want to run an errand, get my car ready. If it's hot in the summer, it cools it down. If it's cold in winter, it warms it up. And it calls you back in 1 minute or 2 minutes and says, we're ready. Are you coming? In a gentle way. And then you get into a conditioned car. Okay? And you can't do this in an internal combustion engine car because the carbon monoxide is bad for you. But in a battery-operated thing, especially when it's plugged in, you actually want to condition the environment before you get it. So there's all sorts of things you can do with electric vehicles. You've got to reduce the price. You've got to make a lot of other things happen. Will this happen? I don't know when it will happen. It will happen, whether it's 10 years from today or 15 years. It won't be 5 years, because it takes 5 years from the time it gets into a company to the time a car manufacturer will put it in a car because of the safety issues. Okay? It has to be really tested very, very well. But, I'm hopeful. What about summer-winter storage? Batteries aren't going to do summer-winter storage. So what do we need for summer-winter storage? Well, remember, 20 years from today, electricity for renewables is going to be really inexpensive. Really, really inexpensive. So let's bank on really cheap electricity. Can you turn that electricity into hydrogen? And you can capture carbon dioxide from a coal plant, a cement plant, a natural gas plant, a steel plant, coking plant, and maybe even the air, which we may need. And you bring that carbon dioxide with the hydrogen and make a liquid hydrocarbon. The advantage of a liquid hydrocarbon is immense, because you can put it on a tanker and you can ship it anywhere around the world. Oil ships for about $1 a barrel anywhere in the world. And so the long-distance transmission line, transcontinental, across the Pacific Ocean, across the Atlantic Ocean, is a tanker. When the fuel arrives at the country, you put it in storage tanks. And so that's also good, because you can store we have 6 months of oil reserves in the United States, just in case there is another oil shock and there's another oil embargo. So the developed countries have roughly a half a year supply of oil. You can have a half-year supply of electricity generating fuel as well. So what do you need to do this? First of all, I like it because you're recycling carbon. So you take carbon, you turn it into fuel, you generate electricity, you make a liquid hydrocarbon for transportation, you recycle the carbon. So you have the captured carbon dioxide, and you take cheap energy or clean forms of energy, and I don't care whether it's electrochemical, photochemical, biochemical, thermochemical, and can you make hydrogen? You need to make hydrogen about $1.50 a kilogram, We're about $5 a kilogram, so it's not competitive. So all this has to be done at this price point. When it's that price point, you've got what Sheikh Yamani was afraid of or dreaming of, depending on your point of view. You have a better solution, okay? So now, we don't have the technology for this today. This is the real challenge of the 21st century. Solar and wind are on track to become super cheap, but you need a liquid hydrocarbon to be shipped around the world and made from cheap, clean energy. Once you have that, then you can go off nuclear, you can go off fossil, you can go off everything else, okay? But you need that. All right, so I'm going to wrap up. I'm already an hour. And so while I was Secretary of Energy, I started a number of things, very innovative funding program called ARPA-E, a revitalized a solar program. EV everywhere is electric vehicles everywhere. And I used to tell the folks at the Department of Energy that I recruited and my recruits helped recruit, that the greatest danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. That's something I tell my students and postdocs in my group. Michelangelo happened to say that. But if you go through life and you haven't failed, that was your single biggest failure in your life, because you didn't try hard enough. You should fail 3/4 of the time, but fail fast and move on. Now, I really enjoyed being Secretary of Energy. My wife, after 4 years, she moved with me to DC, and she said, you know, Steve, no one's irreplaceable, not even you. I know you want to stay another term, I know, or at least a couple more years, but it's time to move back to California, and I'm going. All right. So, especially in the same breath as no one's irreplaceable. So, so there's parts I didn't like. The part I liked the least was having to deal with the press, because they are always trying to play gotcha. You know, they're trying to take a quote out of context, and if you don't give them a quote out of context, they kind of tend to make up stuff. And anyway, so finally, and I told the president, I'm sorry, my wife is, I understand. So we talked about what to do. You know, I left, but he knew a couple months beforehand. But finally, February 1, I announced to the public that I was stepping down, and wrote this long letter that you can Google to the employees about this. And then February 7, 6 days later, The Onion came up with this story. And the story is, hungover energy secretary wakes up next to solar panel. I'll read you part of the article. Sources have reported that following a long night of carousing in a series of DC watering holes, Energy Secretary Stephen Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. Going on saying, I didn't even remember the manufacturer's name. According to sources, Chu's encounter with the crystalline solar receptor, silicon solar receptor, was his most regrettable dalliance since 2009, with an extended fling with a 90-foot wind turbine, nearly ended his marriage. So I walk into work February 7th in the morning, and the head of public affairs says, we normally don't answer reports like this, but maybe we should. So I said, sure, we're going to. So by noon, we issued the following press release. It says only part of it. I just want everyone to know that my decision not to serve a second term as Energy Secretary has absolutely nothing to do with the allegations made in this week's edition of The Onion. While I'm not going to confirm or deny the charges specifically, I will say that clean, renewable solar power is a growing source of U.S. jobs, and it's becoming more and more affordable. So it's no surprise that lots of Americans are falling in love with solar. So they would not let me say, regardless of your sexual orientation. So, anyway, there were limits. So, in closing, I want to remind you of this beautiful photograph taken of Apollo 8. It's the first Apollo mission that orbited the moon in preparation for the moon landing, went around the moon 4 times. And the last orbit, they turned the capsule earthbound, and one of the astronauts took this picture. And he said of it, we came all this way to explore the moon. And the most important thing is we discovered the Earth. Now, let's look at this picture. Christmas Eve, 1968. This is not a good place to live. From that vantage point, this is a pretty good place to live. Guess what? There's nowhere else to go. Since 1968, we have very, very strong evidence. Not only is the climate changing, but it's changed due to humans, and the trajectory we're on is a very bad trajectory, okay? And there's nowhere else to go. So that's, and you're not allowed to say, I like smoking. It's not my problem. And so we do have a moral responsibility, because the most innocent victims to climate change are the poorest people, had nothing to do with any of this, and the people yet to be born. So I close with remind you of an ancient Native American saying that says, we do not inherit the land from our ancestors, we borrow it from our children. Thank you.
So, because it's a little late, we're going to skip questions and answers, but ask the kids come to take a picture with you. Is that okay?
No, well, it's up to you. We're having a debate as to whether, because we're running a tightly scheduled thing, as to whether we should just move on or answer a few questions or answers. Questions?
I'll tell you what, he wants to answer a question. Is there a young person with a question? Is that person really young? I can't see.
Yeah, they're... Yes.
Give that person a microphone. Here comes the microphone.
It's a prepared question?
Thank you. First of all, I would like to say thank you very much for your very informative presentation. I enjoyed it a lot. So my question for today is, what would be your response to the people who say that global warming is something that is not real?
Well, this lecture is my response. I think it's very real, and again, I will stress that what will actually happen in the future, we don't know. There's big uncertainties. In large part because we don't know how the world's going to react to that, and as well as just the science of how the Earth will react to whatever carbon we do put up and have put up in the atmosphere. But the risks are very, very real, and there is no way, and we're talking about a 50% chance of staying below 2 degrees. And we've got 30 years before we run out of that. A 50% chance. So this is not, I'm not talking about a 1% chance. I'm talking about more than likely we go into this very bad, and even 1 degree hotter than we are today is already very bad. So those risks, you don't live your life saying, there's a 50% chance the airplane is going to crash. It's okay. Unless you can assure me that the airplane will crash, I want to visit my parents. You would not get on that airplane. You would not get on the airplane if there's a 10% chance. You would not get on the airplane if there's a 1% chance. And we're talking about 50% chance, but I think we're going to go well above that. So it's very real, and one has to do something about it, and you can't give up because of your generation and your grandchildren's generation.
So as Dean of Physical Sciences, I have a job to do a little salesmanship. And so I want the young people in the room to think about joining us at the University of California to be part of the solution. invent the technology, invent the batteries, invent the transmission lines that are going to be a huge part of this solution. And in a minute, I'm going to invite those young people to come up and have their picture taken with Dr. Chu, so that when they do these inventions, they can say they were motivated by tonight's lecture. Now, for those of you who are too old to be part of that solution, I invite you to go out in the lobby and fill out a pledge form for the School of Physical Sciences and help us educate these young people. So would the young people please come up? Thank you all for coming tonight.
That was spectacular. Thank you so much.